Okay, so we're going to shift gears a little bit here for the last section of the unit. We've been talking about algebraic graphs so far, and today we're going to talk about informational or statistical graphs. I know our next unit is on statistics, but the graphing part we're going to talk about in this unit. So if we are told, well, let's say we are told that out of a group of patients, say their diagnosis, their issue is heart, lung, liver, or stomach. Frequency just means the number that fit into each of those categories. So let's say the frequency, number of heart patients we have at the time is 12. Number of patients with lung problems is 8. Liver problems is 5, and stomach problems is 25. There are several ways we could display this. One way we could display this is in a bar graph. Now, a bar graph can go a couple of different directions. It can be vertical, and statistically, we generally prefer vertical bar graphs. In a vertical bar graph, we put our categories across the bottom. So heart, lung, liver, and stomach. And up the side, we have to make a scale. That scale has to cover all of the possible numbers. Our smallest number is 5, our largest number is 25, so we have to make sure we get to at least 25. So I'm going to label it. I don't have to label it by ones, because that would crowd my graph. I'm going to label this just by 5. So 5, 10, 15, 20, 25. So now I'm going to put my bars on the graph. Heart is 12, so that's going to be somewhere right in here. Lung is 8, so that'll be somewhere in here. Liver is 5, so that's right here. Stomach is 25, so that's all the way up here. So now looking at this graph, there are several things we can pick out very, very quickly. One thing we can pick out very quickly is what is the largest, or which one is the most common. We'll look at the graph, I can very quickly find that is stomach problems. The most number of patients have been admitted with stomach problems. What is the smallest category? Well, the fewest number of patients have been admitted with liver issues. Also, I can tell, are there more, and I'm going to abbreviate here, patients with heart problems or lung problems? Well, I can look very quickly and see the bar for heart is bigger than the bar for lungs, so there's more with heart problems than there are lung issues. So a graph, especially a bar graph, is very good for finding largest, the smallest, and comparing two to see which one is bigger between the two of them. A graph is not great at finding exact values. This one wouldn't be too bad if I wanted to know, without the table here to look at, if I didn't have that over there, if I wanted to look at it and say how many patients have been admitted with lung issues, if I could trace that over and probably be relatively confident that means 8. But what if this weren't 8? What if it were 800? Well, now if I trace it over, well, is it 800? Is it 810? 805? Getting an exact value off a graph is difficult to do. So graphs are not good for exact values. If I wanted to know the exact value for any condition, I would want to go to the table and read the number. Now I said this was a vertical bar graph, which implies that there is a horizontal style bar graph. And a horizontal bar graph is just the same graph turned on its side. The categories are now on the left side here. Heart, lung, liver, and stomach. And numbered across the bottom here. I still have to make sure I number all the way up to 25. Because my largest value is 25. Heart is still 12. So straight up from 12. Lung is still 8. Liver is still 5. Stomach is still 25. So you can see the same things there. Now, one thing I was careful to do when I made both of these graphs, I didn't necessarily do the greatest job of it, but I was careful to try to make the bars about the same width. Because if I had done this, let's say instead of making this one like that, let's say I made it like that. Looking at it, if you think about it, we see that it is still just the height that matters. But what does your mind think when it sees that huge wide bar like that? Well, your mind tends to think, yeah, it's bigger in both directions. It's way more than just double the heart. It's wider as well. So you have to be careful not to do deceiving things like that. There's a lot of people use three-dimensional graphs and stuff like that where, let's say I want to compare A to B, and A has a frequency of 4 and B has a frequency of 8. And I'm oversimplifying this a little bit. So here's A, here's B. 2, 4, 6, 8. So B, do it like this. So A is a frequency of 4. That's where the top of that front bar is. B has a frequency of 8. Well, does B look like it's twice as big as A? No, it looks like it's 4 or 8 times as big. Because it's bigger, it's wider and deeper as well. If I just had a simple bar like that, now it's pretty obvious that the B is twice as tall as A. So be careful with those. Those other things that make a graph pretty can sometimes make it deceiving as well. Another thing with bar graphs that's sometimes deceiving would be this. I'm going to be really creative and just label my categories A, B, and C. Looking at this bar graph, it looks like C is almost double, if not double, B, doesn't it? Because it's twice as tall. But if you look closely here, of the numbering, B is somewhere between 313, 314 in there, and C looks to be about 322, 323. So I call that 313 and 323. Not a huge difference between them. Why does it look so great? Because of this symbol right here. It's a break in the scale. Now the purpose for that is to make it easier to see the difference between them. But it also can be deceiving. It makes C look like it's twice as large, as we said. In reality, if we didn't have that break in the scale, this graph would look something like that. I mean, C is still the tallest, but you can see in this graph that they're all really close to the same size. Okay, other types of graphs we'll want to look at. A big one is a pie graph, or sometimes called a circle graph. Pie graphs and circle graphs usually represent percents. For example, you might get a graph like this. Where you're told that, see, patients that are in are, patients that are currently admitted, outpatient is 20%. Expected to stay only 1 day is 38%. Expected to stay 2 days is 13%. And expected to stay more than 2 days is, got to make sure that works right, 29%. So you might get asked, out of 310 current patients, how many are outpatient? If I look at the graph, outpatient makes up what percent of my total patients? 20%. So I have to find 20% of my 310. So 20% is 20 out of 100. How many is that going to be out of 310? So 20 times 310, 6,200 divided by 100 is 62. So 62 of them are outpatient. To make a circle graph, you have to be able to work with the percents. So let's look at specialties. So out of a group of students, let's say that we have, and I realize these aren't necessarily the specialties for nursing, but we're going to throw in specialties of OB, orthopedic, and just emergency. And our frequency or number of students in each, let's say that we have 18 that are interested in OB, 24 that are interested in ortho, and 8 that are interested in ER. To make a circle graph, we need to know the percent. To find the percent, we first have to know the total. So if I add those all up, I get 50 total students. So then to find the percent for each, well, blank out of 100 equals, for OB, there's 18 out of the 50. Cross multiply and divide there, I'm going to get 36%. For ortho, blank out of 100 equals 24 out of 50. If I cross multiply and divide there, I get 48%. And for ER, blank out of 100 equals 8 out of 50. Cross multiply and divide there, I get 16%. So I have 36%, 48%, and 16%. What should those percents add up to? 100%. Now, they might not always add up to 100%. It might be 99.8 or 100.2 or whatever, if there's rounding in those percents. These all came out perfectly, but if there had been a total of 30, they might be, 0.333, 0.666, whatever. So, I mean, it is possibly slightly off from 100%. To make the circle graph now, or the pie chart, however you want to refer to it, years ago, we would have used these percents to find how many degrees out of 360, find 36% of 360, get the number of degrees, and we take a protractor and measure out the angle and do it perfectly. Well, right now, if we want a graph that's that perfect, I can go into Excel or in several other programs, and it'll spit out a perfect graph in seconds. So for our purposes, all we really care about is getting it close, and we'll go by benchmarks. If I can get through the center of the circle here. Half of the circle is how much? What percent? 50%. A quarter of the circle is 25%. So we should be able to go off of those benchmarks and get fairly close to all of what we have. So do any of those look close to either 50 or 25%? Yeah, ortho is 48%. So I'll make them just smaller than 50. So ortho is 48%. Now the 36 and the 16, kind of a horse apiece. 16 is about 3/5. I could break this 25 up into 5 if I wanted to. If I broke it up into 5 equal sections, each of those sections would be 5%, right? Well, 16 is just a little bit more than 15%, so a little bit more than 3 of them. So somewhere in here would be that 16%, that is ER, 16%. So the rest of this over here has to be OB, which is 36%. So we've constructed it's a little rough, but it's good enough for doing it by hand. Like I said, if we wanted it perfect, I could pull up Excel. What were my numbers again? 18, 24, and 8. And literally in seconds have pretty good pie graph. Okay, enough of that. Another graph we have to be able to read is a line graph. So what we've been looking at so far, these all have shown a snapshot, values at a given point in time. Comparing right now, the students right now, or comparing, we go way back up here, the patients that are in the hospital that are admitted at that point in time, what their ailment is, what category their ailment falls into. A line graph follows a variable over time. So rather than comparing several different categories, they're only looking at one category over time. So for example, let's track number of patients in the ER by day. Now I'm just going to label them day 1, 2, 3, 4, and 5 just to show my creativity. Number of ER patients. So let's say on day 1, the first day that we're tracking it, there are 52 patients that come through the ER. Day 2, 59. Day 3, 38. Day 4, 32. And day 5 is 63 patients. So for a line graph, our time always goes across the bottom, our time progression. So day 1, 2, 3, 4, and 5 go across the bottom. So then our other number has to go up the left side. So we'll leave them 10, 20, 30, 40, 50, 60. So day 1 was 52. That'll be somewhere in here. Day 2 is 59. That's just below 60. Day 3, it dropped to 38, somewhere in here. Day 4 is down to 32. Day 5 is back up to 63. So we connect those dots with lines. Maybe 5 a little later, so off over there. There. The line graph, just like a bar graph, can be used to pick out highest and lowest points. The day that had the fewest patients admitted to the ER is obviously day 4. Day with the most might be a little tough to pick out between 2 and 5, but 5 had more. But the other thing that's significant on a line graph is not just the height of that point, but the slope. There are 2 spots on this graph that have a positive slope. Right here and right here. Positive slope means the number is increasing. So from day 1 to day 2, the number of patients admitted increased because the slope is positive. From day 4 to day 5, it increased because the slope is positive. A negative slope means, of course, it is decreasing, getting smaller. So between day 2 and 3, it decreased because it's a negative slope. And between day 3 and 4, it decreased because there's a negative slope. The other thing from the slope is the greater the slope, the steeper the line, the faster it is increasing or decreasing. So if I ask you between what 2 days did it increase the most or the fastest, that's pretty obviously right here between day 4 and 5, because that's where that line is significantly steeper, going up. If I asked you between what 2 days did it decrease the most or the fastest, again, that's between days 2 and 3, because that is a negative slope, and it's obviously the steeper of the negative slopes. So a line graph can be used for picking out those trends and changes very quickly as well. Okay, so from last week, a couple of things to review before we wrap it up here. So let's say you hang a bag with 600 milliliters of fluid, just with 600 milliliters. In 3 hours, there are 150 milliliters left. What is the flow rate? Well, we could graph this if we wanted to. At time 0, that's when you started. You had 600 milliliters of fluid. At 3 hours, you had 150 milliliters of fluid. We're assuming since it's an IV, it's going to flow at a linear rate, a constant rate. If I want to know what the rate is, it is just the slope of this line. I could find the slope off the graph, drawing my rise and my run. This has gone from 600 down to 150, so that's a negative 450 milliliters in 3 hours. So the bag has emptied at 450 milliliters over 3 hours. The medication has flowed into the patient at a positive 450 milliliters over 3 hours. We divide that out to get 150 milliliters per hour. Another way we could have handled this is we could have just made coordinates, ordered pairs. At time 0, there's 600 milliliters. At time 3, there's 150 milliliters. Remember our formula for slope. The y-coordinate of 0.2, which is the 150, minus the y-coordinate of 0.1, which is 600, makes my rise. On bottom for the run, x-coordinate of 0.2 minus the x-coordinate of 0.1. 150 minus 600 is negative 450. 3 minus 0 is 3. So that is a negative 150 milliliters per hour. Now that's the rate that it's flowing out of the bag. The rate that's flowing into the patient, of course, would be the positive of that. So let's look at milliliters of medication that's flowed into a patient per hour. And let's say our graph looks like this. So if I were to ask you some questions about this graph, the first one being, at time 0, or t equals 0, or 0 hour, whatever you want to describe it, how much medication was in the patient? So when we started keeping track here, how much medication was already in the patient? Not 20, but careful. 40, right? 20, 40, 60, 80, 100, right? So 40 milliliters. The starting amount, or when x is 0 or t is 0 for time, is what we call the y-intercept again. So the y-intercept is that initial amount, 40 milliliters. If I ask you, what is the rate of change? How fast is it changing? Well, I find 2 points. I just will use the y-intercept and that one, and I find the rate that it is changing. Well, it goes up from 40 to 100 is how much? That's 60 milliliters over 1, 2, 3, 4, 5 hours. So the rate of change here is 60 milliliters over 5 hours, or 12 milliliters per hour. The rate of change is just what we've been using as the slope for our generic graphs. So the y-intercept is the starting point. The slope is the rate of change. So if I am told, describe the amount of medication in the patient in an equation, or write an equation to describe the amount of medication in the patient. Either way works. What's that equation going to look like? Remember, it's y equals slope times x plus my y-intercept. So what's going to go in front of x? The slope, 12. Now I could write 12 milliliters per hour times x, but I don't need the units in there. What's going to go in here for the y-intercept? 40. So that equation describes the amount of medication in the patient. So I might ask, how much medication is in, I know this is very poor terminology, but is in the patient after 3 hours? Well, the 3 is going to go in for x. So y is going to be 12 times 3 plus 40. 12 times 3 is 36, plus 40 is 76. So after 3 hours, there are 76 milliliters of medication in the patient. I could ask, how long will it take, or at what time to get to, no, what do I want to put in there? 124 milliliters in the patient. So at what time will there be 124 milliliters of medication in the patient? Now the 124 is not X, it is Y. It's the amount of medication. So the 124 goes in for Y in this equation. So it's 124 equals 12X plus 40. Because X represents the time, so we have to solve for X. So subtract 40. 84 equals 12X. And divide by 12. So 7 equals X. So at 7 hours, there would be 124 milliliters in the patient. Any questions? I'm going to have you guys try one like that last one. So, we'll label this hours again in milliliters. Give you that graph. And we're going to ask you what is the level at t equals 0 hours? 2, what is the rate of change? 3, describe the level with an equation. 4, now t equals 0, that could also be x equals 0 if you wanted to use x for that, by the way. Find the level after 5 hours. And finally 5, at what time will the level equal 0? So I'll give you guys a few minutes to work on those, and then we'll go over them quick. Let's go over the first couple, just make sure you're on the right track. What is the level at time equals 0 or x equals 0? What did you get for that? Well, 100, 20, 40, 60. 160. 160 milliliters. That, remember, is the y-intercept, the initial amount. What is the rate of change? Well, it goes between 2 points that I can identify, or 2 coordinates on the graph, sometimes called lattice points. It goes down how far? That represents 40 milliliters over 3 hours. So that's 40 milliliters over 3 hours. It is going down, so it's negative. So that's a negative 13 1/3 milliliters per hour. Or if you'd have left it as a negative 40 over 3, that would be acceptable as well. So that makes the equation y equals What multiplies the x? The slope is the negative 40 over 3. That multiplies the x. Or the negative 13 1/3. The rate of change, or the slope, always multiplies x. Then the starting point is the 160, so that's plus 160 at the end. So now from that equation, I'll give you a couple more minutes to solve 4 and 5. So find the level after 5 hours. You're going to put 5 in for x. So that ends up being negative 40 over 3 times 5 is a negative, that's 66 2/3 plus 160. So that's going to be at 93 1/3 milliliter. At what time will the level equal 0? You'll put in 0 for y. Negative 40 over 3x plus 160. And we'll solve that by subtracting 160 first. So negative 160 equals a negative 40 over 3x. And we divide by negative 40 over 3. So over there we have x. Negative 160 divided by negative 40 over 3 is 12. It's 12 hours to hit 0. Okay, we are out of time. So the stuff that is new from today, page 231 to 235, 1 through 9, and page 240 to 241, 1 through 21, the odds. Obviously next week, there's no class because of Thanksgiving break, so it'll be 2 weeks, which I believe is December 3rd, is it? December 2nd. That'll be our test on graphing. Now, this is one of those tests that most of you will get done in about an hour and 15 minutes, but there's usually a few that take about an hour and a half, hour and 45. So trying to squeeze in a lecture afterwards is a little tight. So what I will do for this one is I will actually post a video of some introductory stuff for statistics. If you would watch that video before you come then on the 9th, so that in the 9th, in that 2 hours on the 9th, we can get through the material we need to for statistics. So mostly what the video will be is just vocabulary and stuff like that for statistics that you'll have. So there won't be a lecture in that next class, but there will be a video for you to look at just to be ready and up and running. Okay, well, with that, you guys all have a great Thanksgiving, and we'll see you in 2 weeks.